Welcome to this presentation on linked list group rewards problem. Today we will explore the problem and the solution to rewards every k nodes in a linked list, a key concept in data structures. The task is to reverse every k nodes in a linked list. If the number of nodes is not a multiple of k, we reverse the remaining nodes as a group. Let's look at some examples. In the first example, we have the list 1, 2, 2, 4, 5, 6, 7 and 8 with k equal to 4. The first group of 4 nodes 1, 2, 2 and 4 is reversed, followed by the second group of 4 nodes 5, 6, 7 and 8. Resulting list is 4, 2, 2, 1, 8, 7, 6, 5. In the second example, with k equal to 3, we reverse the first group of 3 nodes 1, 2, 3, resulting in 3, 2, 1. The remaining nodes 4 and 5 are reversed as a group, producing the final list 3, 2, 1, 5, 4. The problem has some constraints. The size of the linked list is between 1 and 1 lakh. The data values of the nodes range from 1 to 10 to the power 6 and the value of k is between 1 and the size of the list. Let's now look at an overview of the approach to solve this problem. First, we will traverse the list in groups of k nodes. For each group, we reverse the nodes. Then we connect the reversed groups together. Finally, if there are fewer than k nodes left at the end of the list, we reverse them as well. I will show you an illustration to help visualize this process. Now let's move to the code. First, we check if the head of the list is null. If it is, we return the head immediately. Then we initialize 3 pointers: car to traverse the list, new head to store the head of the reversed list, and tail to keep track of the end of the reversed groups. Inside a while loop, we continue traversing the list until we reach the end. For each group of k nodes, we initialize 3 pointers: group head, priv, and next node. We then reverse the nodes in this group. To do this, we adjust the next pointers of the nodes, ensuring that the nodes are reversed one by one. Once a group is reversed, we handle the connections. If new head is still null, we set it to priv, which points to the head of the reversed list after the first group. We then connect the previous group to the current reversed group. Finally, we move the tail pointer to the end of the current reversed node. Here is the complete code for the solution. It's a combination of the steps we discussed: traversing the list in groups, reversing the nodes, and connecting the reversed groups. The function returns the new head of the reversed list. Let's discuss the time complexity. Reversing each group takes big of k times, and since we traverse the entire list once, the overall time complexity is big of n, where n is the number of nodes in the list. The space complexity is big of 1, as we are performing the reversal in place without using extra space. Here's a visualization to better understand the reversal. Initially we have the list 1, 2, 3, 4 and 5 with k equal to 3. After reversing the first group of the 3 nodes, the list becomes 3, 2, 1, 4, 5. After reversing the remaining nodes, the final list is 3, 2, 1, 5, 4. To summarize, the key points are: this approach efficiently reverses groups of nodes in a linked list, handles edge cases like the last group with fewer nodes, and demonstrates how pointer manipulation is essential in linked list problems. That concludes the presentation. If you have any questions, feel free to ask. Welcome to the presentation on grid game problem. In this problem, we are tasked with optimizing the score of robot 1 while minimizing the score of robot 2 using a 2D grid. Let's dive into the details. In this problem, we have a 2 cross n grid filled with non-negative integers. Two robots start at opposite ends of the grid, robot 1 at 0, 0 and robot 2 at 1 and minus 1. The goal is to maximize robot 1's score while minimizing robot 2's score. Both robots pick up all points from the cells they pass through, and we must minimize the maximum score collected by robot 2 as robot 1 plays optimally. Let's visualize the problem with an example. Consider a 2 cross n grid where each cell contains points. Robot 1 moves from left to right along the top row, while robot 2 moves from the right to left along the bottom row. Both robots picks up points from the cells they visit. The challenge is to find a strategy where robot 1's path minimizes the maximum points robot 2 can collect. To solve this problem effectively, we can break the approach into few key steps. Prefix and suffix sums. We will pre-compute prefix and suffix sums for both rows to calculate scores quickly. Simulating robot 1's path. We will simulate all possible columns where robot 1 could switch from the top row to the bottom row. Minimizing robot 2's maximum score. We will track the minimum of the maximum scores that robot 2 can achieve based on robot 1's move. We begin by computing prefix and suffix sums for the rows. The suffix sum for the top row gives the total points from column I to n-1. Similarly, the prefix sum for the bottom row gives the total points from column 0 to I. These pre-computations help in calculating scores efficiently during the simulation. Next, we simulate robot 1's path. Robot 1 can switch rows at any column, and we calculate the resulting score for robot 2 based on where it moves. If robot 2 moves along the top row after column I, we use the suffix sum for the top row. If robot 2 moves along the bottom row before column I, we use the prefix sum for the bottom row. To minimize robot 2's score, we need to find the column where robot 1 should switch rows to minimize the maximum score robot 2 can collect. By trying all possible switch points, we can calculate the maximum score robot 2 can achieve and track the minimum of those maximum scores. Here's the C++ code for the solution. We start by defining the suffix and prefix sum vectors, which will store the computed sums for the top and bottom rows. We loop through the grid to compute the suffix sums for the top row and the prefix sums for the bottom row. In this part of the code, we compute the suffix sums for the top row starting from the last column. Similarly, we compute the prefix sums for the bottom row starting from the first column. These sums will be used later to compute robot 2's score. Now we iterate over each column to simulate robot 1's path. For each column, we calculate the maximum score for robot 2 either from the top row or bottom row and track the minimum of these scores to get the optimal solution. Let's break down the code. First, the suffix and prefix sums help us efficiently calculate the remaining score for robot 2 after each possible switch point. The goal is to compute the minimum of the maximum scores robot 2 can get, ensuring robot 1 plays optimally. Let's talk about the complexity. The time complexity is big of n because we make two passes through the grid, one for computing the prefix and suffix sums and another for calculating the result. The space complexity is big of n due to the storage of the prefix and suffix sums. In conclusion, the grid game problem can be efficiently solved using prefix and suffix sums. The approach minimizes the maximum score that robot 2 can collect by simulating all possible switch points for robot 1. The solution is optimal for large grids with a linear time complexity.